2023 Jan, Unit 4, question number 17. So I want you to pause, read this question, and then we're going to get to solving it. Okay, so I hope you have read the question. So basically what we've got the electron being accelerated through the anode. It's going to be released from the cathode through thermionic emission, and then the electron passes straight through, and we've got a magnetic force and an electric force that are acting on the electron, and the electron passes straight in a straight line. Because of this, we can say that the magnetic force is equals to the electric force. Okay. Now, what we can do is we know the magnetic force is equals to BVQ sine 90, and the electric force, since these are metal plates that are producing the electric field will be uniform. So we're going to get EQ, and then E is equals to V by D. So we can get BVQ sine 90 is equals to V by DQ. Now the charge here is electron, so both those Q are going to cancel out. This is just 1, so that also cancels out. So we get BV is equals to V over D. Bear in mind, this is the velocity of the electron, and this is the potential difference across the metal plates. Now I'm going to make this a subject, so we're going to get V is equals to capital V over B times D. And there you go. Okay, next part. They just want you to plug in the values, get the answer. So V is equals to capital V, B times D. So 231 over 5.5 times 10 to the raised power of minus 4 times 1.5 times 10 to the raised power of minus 2. So we're going to get 2.8 times 10 to the raised power of 7 meter per second, which is approximately 3 times 10 to the raised power of 7 meter per second. Okay, now we've got the third part of the question, which says when the electric field between the plates is removed, the electrons now move in a circular path due to the magnetic field. And then they've given you the charge per unit, per unit mass of the electron. And they want you to deduce whether the charge per unit mass of the electron calculated using the data from this experiment is consistent with the accepted value. First thing we know is that the magnetic field is going to be causing the circular motion, so the magnetic force is equals to the centripetal force. So BVQ sine 90 is equals to mv square over r. The v cancels out with the v square, and we're going to end up with BQ is equals to mv over r. R is equals to mv over BQ. I'm sure you're familiar with this formula. Now I'm going to do is I'm going to make the charge over mass the subject. That's what my aim here is going to be. So I'm going to move charge to the other side. So Q, and then mass also to the other side. So I'm going to get M times R is going to be equals to V over B. I hope that makes sense. I moved the charge and the mass to the other side, and I'm going to move the radius to the other side. So we're going to get Q over M is equals to V divided by RB. Okay, I hope that makes sense. Let me erase all of this. Okay, now we're going to end up with this. I'm going to plug in. Now the velocity here is the velocity that we had here. Okay, that was the velocity of the electron that was moving through, and it's going to be the same velocity here as well. Okay, so that's going to be 2.8 times 10 to the raised power of 7 divided by 39 times 10 to the raised power of minus 2 times 5.5 times 10 to the raised power of minus 4. That's going to get you 1.305 times 10 to the raised power of 11 coulomb per kg, and that's going to be less than 1.8 times 10 to the raised power of 11 coulomb per kg. So it is not consistent with the accepted value. So not consistent with accepted value. That's going to be the answer.
So that's the thing wired up and it's ready to turn on now. And I'm going to start by switching on the cathode, which takes a little while to warm up, but there you go, you can see it starting to glow now, which means you can turn on the high voltage supply. And I'm going to turn that up to about 3000 volts. Now, what I hope you can see is a green dot surrounded by fainter concentric green circles. And that's a diffraction pattern that's produced as the electrons fly through the graphite. Now, you can increase the energy of the electrons by increasing the voltage. You can see that's changed the diffraction pattern. The rings are closer together. And that's because at increased energies, the electrons have a shorter wavelength and they're diffracted less by the graphite. There's one more thing you might want to do with this apparatus, and that's to convince your students that the pattern is genuinely produced by electrons, that is, charged particles, and not by a beam of light. And to do that, you use a magnet. And if you bring that close to the beam, you can see that it deflects the image on the screen. And that certainly wouldn't be happening if it was being produced by a beam of light.
Okay, so the next part, which is the last part of this question, says in 1927, J.J. Thomson's son directed beams of electrons at thin films of metal. The photograph shows one of the patterns observed. Explain how this pattern changed scientists' understanding about the nature of electrons. Well, let me just write the answer down first. Now, if you see this pattern, it is a diffraction pattern. So we have got a diffraction pattern is observed. That's the first mark you get. The second mark you get is for saying that diffraction occurs in waves only. And that would suggest that electron has a wave nature. Electron has a wave nature and can behave as a wave. Now, before this, the scientists, they thought that electron was just a particle. But through these experiments, we came to understand that electron is not only a particle, but has a wave nature. It has a dual nature, right? Dual nature. We also call it the wave-particle duality. Now, this question tests your quantum physics from your A2 level for Cambridge students and for Edexcel your AS level knowledge from your waves chapter. Okay, so make sure you are strong on all of your chapters because all of the questions, they are a combination of different topics, right? So we saw like above we had a question from magnetic field, then we came to waves, so it's a mixed bag. Okay, that's all for this. Now I'm going to show you the mark scheme and examiner report.